Welcome to the demonstration corner. Today we will be talking about measuring the specific heat and directional thermal conductivity and thermal diffusivity on batteries. We'll show you a basic setup on pouch batteries and a basic setup on cylinder batteries, and just discuss some of the flexibility on different sizes you can do. We'll be doing that on the MP-1 Transient Plane Source method. But before we do that, our classic approach here at the demonstration corner is to show the equipment we have available for demonstrations one-on-one, as well as live demos like this. We also use this same equipment for training. So if we start from this side, this is our guarded heat flow meter following ASTM E1530. This is for measuring complex structures, both in terms of heterogeneity and layers. It's important to think about, when you think of heterogeneity, that it's not necessarily the dispersion of filler under a microscope. It's defined, when you're measuring thermal conductivity, homogeneity is defined as how homogeneous is the sample in terms of the property you're measuring. That's an important principle. So the guarded heat flow meter is a method for looking at the one-dimensional heat flow with a guard that protects against lateral heat loss. So your delta T is across the sample completely. It gives you very high confidence thermal resistance and thermal conductivity. This method goes up to 300 Celsius, control of pressure and or thickness. This is, I should say, also up to 100 watts per Kelvin. Our heat flow meter, we have this in different sizes. The overall temperature range is -30 to 110, or this model right here is -20 to 75 Celsius. Those are plate temperatures. This is for measuring insulation and construction material according to ASTM C518 and related standards. And we have various sizes of that model. So if we come over here, we have our dedicated transient plane source for following ISO 22007-2. Plugged into it is our temperature device for 0 to 100 C. Of course, its basic configuration is room temperature. The basic thermal conductivity range is 0.01 to 100 watts per Kelvin. You can max that up to 500 watts per Kelvin with an upgrade. This measures conductivity, diffusivity, and volumetric specific heat according to the ISO. In addition, you can add modules for measuring anisotropy, thin films, slabs, which is a conductive sheets. It's a fairly versatile instrument. This is the Transient Hot Wire, which follows the testing of liquids and phase change materials according to ASTM 7896. The overall temperature range, now you can configure it differently, but is cryogenic up to 300 C. You can back pressure it up to 35 bar. Of course, we have different temperature ranges within that temperature range. This is an absolute method for measuring thermal conductivity, thermal diffusivity, and volumetric specific heat of liquids. And down the end of the table, we have our small format heat flow meter. It's for measuring small-sized insulation. And then the baby brother to the MP-1 is down the rest of the way. That is our MP-2, which has primary sensors, transient plane source, transient hot wire, transient line source, in an affordable package, but it gives you the ability to make good measurements on primary sensors. We really do try to create a situation where people are using the right method. So what we're going to talk about today is the use of the transient plane source on the MP-1. I'll briefly discuss the overall of the MP-1. So it can be packaged right now. We have the transient plane source, or TPS temperature platform, plugged into it. Of course, you do not have to purchase that. That's for measurement of temperature. The overall temperature for the one that's here is 0 to 300 Celsius, and that can be upgraded to cryogenic as well. The other methods that you can combine with the MP-1 are transient hot wire. There's a matching temperature platform for that, again for measuring liquids and phase change materials, transient line source, and transient hot strip. But if you don't need this particular temperature platform, or if you need an oven, one of the other ovens we offer that you can communicate with the MP-1, that you can certainly acquire just the controller by itself. But you can expand this unit. So this unit has 4 channels, 1 in the front, 3 in the back. We have smart software that allows you to use the same controller to operate up to 4 sensors or 4 chambers, whatever that combination of methods and or sensors that suits your requirement for testing or volume of testing. Today we have several room temperature sensors plugged into the same controller just to allow simple demonstration, but it still does give you an idea on the versatility of having that switch. Some of the other key features of the MP-1 are its high frequency rate. So we have the highest frequency related collection of points so that our data is super stable. This method measures the contact resistance between the sensor and sample. Those are all proprietary capabilities of the MP-1. And Transient Plane Source method on the MP-1. And we'll share a little bit about those. But what we're going to talk today is if your application is the measurement of thermophysical properties of batteries. So we have a battery package that basically puts, depending on your battery type, or if you have both of them, we offer 2 types of specific heat sensors. So as covered, when you're looking at measuring anisotropy, especially by the ISO, it does require the input of specific heat. So the very fact that you have materials that are anisotropic, and what creates the anisotropy is the layers. Most of the pouch materials have multiple layers inside, and of course your cylinder battery has a jelly roll shape of layers. Those are not isotropic samples. So the volumetric specific heat that you can calculate from thermal conductivity and thermal diffusivity is not accurate anymore. You can only calculate thermal specific heat from volumetric specific heat from thermal conductivity and thermal diffusivity when your material is isotropic. So therefore you have to measure specific heat directly. And then that is an input into the measurement of anisotropy. So the typical first step is to measure the specific heat of the sample using our specific heat cells, and then using that as an input for measuring the anisotropic properties for thermal conductivity and thermal diffusivity. So if we bring the camera in, we'll talk a little bit about those cells and how they're used. So here set up is a particular specific heat cell of 1 dimension. As you can see, we have a range of dimensions. So this one is about 95 millimeters wide, and we can custom make these. These are 2 standard sizes. The pouch battery that we're going to test today that we've already measured specific heat on, but you can see that it fits inside the cell. And the point there is we want to measure that entire sample for specific heat. And this one's just twice the width, and that's for pouches that vary in size. And if we look underneath it, we have a sensor that's been designed to cover the entire bottom of the specific heat cell. And then we insulate it during our measurement. I'll show you that setup. We can make these specific heat cells up to 250 millimeters wide and much longer. So the specific heat length, the length of the cell is based off of the length of your pouch. So we try to match it up as best we can. Of course, you can use a much larger specific heat cell for a smaller sample. We try to cover minimum 40 or 50% of the area, but if we can, also you just get more reliable testing if you can look at a specific heat cell that matches your dimensions a little bit better. So you're covering more of the test area. You're just more sensitive to that. So we have the ability, we have standard size cells, and then we can custom make specific heat cells. So if we were measuring the specific heat of this pouch battery, we would run a reference. The reference would be empty, so no sample inside it. And this is configured inside of our room temperature sample holder. This of course could be put in the oven up to 75 Celsius, and then we have upgrade of temperature on the insulation used that would allow that sensor to go up to 300 Celsius and down subambient as well. So we would run this reference empty and then save that reference. You'll see that in the software, and then put your sample inside and repeat that process. And then you would get the software, the calculation would calculate the amount of energy to heat up the sample versus the empty cell. And that's the setup. So with every specific heat measurement, we also offer references. So in this case, like we have a Maycore reference, this can be used to verify operation of your sensor if there's any doubt. So you can, and we have 304 of the same dimension. What's nice about sort of having two very different conductivities is when you're measuring anisotropy, if you have, this is around 13 or 14 watts per Kelvin, this is around 1.5. If you have these very different conductivities, when you go to measure your anisotropy, it does give you confidence that you're able to measure specific heat on such different materials, and the average of something that is layers of such materials. Of course, the layers inside of a pouch battery could be very different types of metal than 304. But these references are quite good for training and verifying operation. So that would be our standard setup for a pouch battery looking at, or even a prismatic battery. We would have to make sure we cover the entire sample with a lid, so we can design specific key cells for that. So for a cylinder battery, and this is 21700 battery, we have a slightly different setup. So if we bring the camera a little bit more this way, sort of turn it, I can show you that. So this is a specific heat setup for a cylinder battery. So we would run the reference. So this is just slightly larger than the cylinder battery itself. And we would run the reference on this cylinder, on this specific heat cell. And then we would place the battery inside that and run against the reference the same setup. Of course, we would insulate it, so when you measure, when you get the specific heat, rather the battery package for cylinder batteries, we include one of these which allows you to insulate the specific heat cell in this shape. They're magnet, and then you place that on top, and then you have an entire insulation for your specific heat measurement. And then the other holes are for measuring the other configuration. So when that is and we can make this of different diameters and different heights. So I think we can go up to 70 millimeters or 80 millimeters in diameter and several heights. So we can accommodate most cylinder size batteries. And then we can custom make any cells to really accommodate most dimensions of a battery cylinder. So that would be your standard setup for specific heat on a cylinder. Now for running thermal conductivity measurements on a cylinder, we would set up an asymmetric experiment where, if I remove this, so let's say we already had the specific heat measurement done. My experimental setup would be with that sensor of cord installed, and then we would be directly connecting the sensor to the underside of the cylinder, and we would be insulating it with the other smaller dimension and looking at the heat propagation along the length of the cylinder. And there's one more configuration. That's a very high confidence thermal conductivity. Of course, you'll get an average of the jelly roll. You'll get an average along the length. There's one more configuration, and that is if looking at the asymmetric or single-sided test of that cylinder. So what we're going to do is we're going to put the sensor in contact with XPS that's been machined out to the radius of the cylinder, in this case 21700. Of course, you would have different dimensions depending on the type of cylinder and size you're measuring. And then we would set this up inside the cell, the sample holder, and your configuration would be sensor and battery. So that would be the configuration. And then we would clamp it together like that, and you would get a single-sided measurement of a cylindrical shape. Now, there's a question that happens, is this is not a flat sample, so how does this sensor and how does the math accommodate the curvature? We have a proprietary curvature for measuring using this method, the Transient Plane Source method, for rounded materials. So there is still some error associated with having a very conductive, in this case there's an insulative layer and a very conductive shell, and then you have jelly roll inside it. There's some small error, but one way of determining is when you measure along the height of your sample, 1D, and you look at this configuration, your in-plane direction is the same direction as that one-dimensional direction, and now you have the additional direction of into the battery. And if you have good correlation between your one-dimensional measurement, meaning like this, like that, and then you have your configuration of single-sided test or asymmetric test where you get this direction and into it, if you have good correlation of this direction of 1D, that's a pretty good indication your values are indicative or somewhat close to the value. So there is some uncertainty caused by the construction of the material testing it this way, but you can get pretty good values. We like to discuss the uncertainty of our measurements. I think it's important to sort of understand that when you're using this data and you expect accurate results. So the other means of determining accuracy is just like with slab or pouch type batteries, we can offer reference materials to be able to verify operations. So this is Macor, and this is again a steel, and we can measure specific heat of each, and these are machined actually in the exact same shape as a 21700 just to give us a very confident dimension, and we can measure the just like for the battery, we can measure in this configuration and one-dimensional and look at how accurate we are. And when we use our curvature correction on these measurements of these homogeneous materials, we get very good results. Without the curvature correction, you do get some effect of that curvature. So the correction is quite helpful in that measurement. So, and then we have two materials that are very different thermal conductivity, and that gives you some degree of confidence in the anisotropy you're measuring. So that's our setup for our specific heat on cylinders and our one-dimensional setup for cylinders. But we're going to show a little setup for, once you have your specific heat on your pouch, how can I make a measurement for anisotropy? So using the Transient Plane Source method, following the ISO, we can do a surface sensor in contact with this, or TPS sensor in contact with this. We're going to do an asymmetric measurement, single-sided, and then we'll go to the software and show you how that measurement is done in the software. So I'm going to change camera angles and just show you the sensor sample setup. So here it's another sample holder we have connected to, you can see that there's several channels in the background there. This is connected to channel 4, and I already have a sensor plugged into the adapter. There's several videos that show those basic functions of the MP-1. I invite you to look at them. So we're going to put the smooth side down on this sample, and we're going to center the sample to the sensor as best we can. And I've already recorded the thickness of this sample because we'll need that as inputs for the setup. And then I'm going to put a protection plate on top so that I don't get any puncturing, because of course if you puncture the pouch, it will affect your results. You'll be letting out gas, especially if you're doing temperatures. And you only need thumb tight. Some of the questions we get when we're measuring batteries is, can we change the pressure? Of course. If you were to take this top bar off, you can use different weights to accomplish that, or we even have compression stands that allow you to precisely measure how much pressure you're applying. So that's a single-sided setup for a pouch, an anisotropic pouch cell. So on the bottom is our XPS. That becomes a known material because we've measured it. We can input that value in the software, and then our sensor, and then our pouch sample. So that's the setup for a single-sided pouch test for measuring directions. So I'm going to change to my desktop. This is our home screen. It shows everything that's plugged into the MP-1. As of right now, we have the temperature platform, which we're not going to use today. We have we've removed the THW temperature platform just to show focus on the TPS method, and we have two sample holders connected. So all of our devices that plug into the MP-1 are auto-identifying. So if we go to our measurement, I've already told it where I want to save the data. We're going to do a 3D measurement, or or average results, bulk results. We're going to single-side it, and we're going to do an anisotropic test of a semi-infinite body. This is the controller, and we're going to do room temperature testing. I'm not selecting one of the temperature devices. And here's our sample input of the inputs that are needed for the measurement itself. So that 2.4 is the specific heat that I've already pre-measured with the pouch approach you saw. I'll show you that data in the analysis application as well. The other material, the known foam, the known insulation that's on the underside of the sensors, XPS. If you were using different types of insulation, you could select them here. This is the sample height as well as the radius of that sample. So this sample is around 41 millimeters wide. It is the 4th channel, port 4, and if we click this button, it is, so let's say I'm on some random sensor. This is the intelligence of our transient plane source. If you click that, it tells you what sensor you should be using. I'm going to do a resistance check on that sensor, which just electrically confirms that the sensor is properly set up and making contact. It'll give us a green light if everything's good. If you mouse over it, you can see the resistance. Temperature is automatic. There's a temperature, a PT sensor inside the sensor adapter, so you don't have to write that in. It's always recorded. The ITPS gives us auto power and time functions. We have several live videos, live demonstrations that we show that function. It's pretty intuitive. It's a proprietary approach to selection of parameters that Thermtest does for the Transient Plane Source method. It's true, this method's been around for about 20 years. I've installed hundreds of these devices over the years, and we would typically train people on manual selection of power, manual selection of time based off of the diffusivity of your material and the dimensions. We've written a proprietary approach to our TPS on the MP-1 that automates all the selection of time and selection of power based off of a continuous measurement. So the instrument makes a continuous measurement. Live is auto-calculating based off of the inputs of only the sample height and the sample radius and the diffusivity that it's acquiring during that continuous measurement. So it'll automatically select power and time based off of the diffusivity and the dimensions of your sample, which is quite a convenient and really intelligent way to make measurements. You can still, of course, do manual inputs. So there's nothing stopping you from selecting manual inputs. So this is the absolute transient plane source following the ISO. So you still have the manual approach as well as automating that. The quick transient that allows us to do a quick measurement and see if the parameters that the ITPS gives us satisfy those input parameters. We won't run that today. We're just going to set up a schedule. So I'm going to do 5 seconds with 250 milliwatts. So we'll go to the next one. And this is where we can run our schedule. So I'm going to do 5 measurements with a 10-minute delay. 5 measurements with 10-minute delay with 5 seconds each at 250 milliwatts. And those parameters are suggested by the ITPS to achieve our minimum temperature rise and our probing depth. So we want our heat to stay within the dimensions of the sample. The anisotropic samples have another layer of slightly more complexity because now we have 2 directions of penetration. We have through the thickness and in plane. We want to make sure we're staying within the dimensions of the sample. And then we're going to have a 10-minute delay before that first measurement. So by clicking Start, it will automatically configure that sensor with those parameters and measure the sensor resistance and start counting down that first 10-minute delay. So that will continue to run in the background. You can see we've made a number of other measurements here using this device. This 5 measurements is the previous 5 measurements on this same sample that I made before the demonstration. You can see here we have our penetration depths. I'll review this in the analysis app. You can see the input of 2.4. Again, we measured that and we'll review that as well. So we get all this data here, and this screen really is the capture of the data as it's being generated. We have a separate application for analyzing and fully understanding the data in a much more convenient way. So here you can see an event log, transient 1, 2, 3, 4. We can review our residuals here to make sure we're getting a good fit. And you can see now this is bulk conductivity, and these are the anisotropic results. So bulk conductivity would be the average between the two planes. So while that is running, you see you can click into any one of them and see the data that was generated. We will let that run in the background. It's now doing a 10-minute countdown. And let's go to the analysis application. So here's our analysis application. And this is the specific heat data on that pouch battery. So we have an average of, this is volumetric specific heat, we have an average of 2.4 megajoules per meter cubed Kelvin. If we select individual ones, we can see the specific heat measured on that material. So that gives you an idea of the specific heat of that battery. So the input we need for the anisotropic module is volumetrics, of course. So it's not just the specific heat; it's the volumetric version. So it's around 2.1, 2.4. So you can see the repeatability of that time. In this case, we did a 640 seconds reference and calibration, and we input the volume and the mass. So it's around 2.39, 2.4. That's the input we used. For reference, we measured Maycore as well, just for our own sort of verification of the reference. You don't have to do that, of course, but we wanted to do it. And you can see that our average volumetric specific heat is 2 on Maycore, and the individual specific heats, which is joules per kilogram Kelvin, is 826, and that's within that's a pretty good correlation to the known value of Maycore. Again, this is on the Maycore that is of a similar dimension to that pouch. So it's roughly 120 by 42 by 9 millimeters thick, roughly. So that gives us a good confidence in that our specific heat sensor is working well and that our parameters are working well. And you can basically you can run a reference at different times and always have it available to run different unknown materials against it. So we're going to show our pouch battery data. So this is our 5 seconds at 253, which is the same as 250 milliwatts. You can see our bulk, that's our bulk data. And then if we select one of them, you can see our axial value of conductivity, so roughly 1.76 watts per meter Kelvin through the thickness, and our diffusivity, and our in-plane conductivity and diffusivity. And these are our bulk values. That's what you see here. And that 2.4, that was the input from the specific heat measurement we made independently. So it's a two-step measurement to measure all the properties associated with the pouch. And if we select all of them, you can see the bulk average and the repeatability of it. But then if you select individual ones, you can see the different results. And the repeatability is pretty good. If we select all of them, we can look at the residual pattern as well, so we have a good fitting. We are taking the number of points in this 5-second measurement is 500, so it gives you an idea on the population of points. That gives us a lot of confidence in our results. And in addition to the directional properties, we get our indicators of quality, and that's the basic measurement of a pouch battery. And we have data on, if you're interested in seeing what the data looks like on the cylinder battery, both specific heat and directional properties. So on the cylinder batteries, we would be reviewing one-dimensional data as well as anisotropic data. So there's another set of data to review on that, because you can align the sensor with the diameter of the sample to get the along the height thermal conductivity and diffusivity. That is the basic demonstration. We can, of course, from here, we can export all this data to Excel and see it all in a nice, convenient location. Yeah, and this is our transient analysis. So in the background, our tests are still being done, or the countdown. And if you want to see that, I can actually right-click and cancel. Let's do this. We have a few moments. We can skip stabilization. It'll go right into recording drift. So in advance of every measurement of transient, it does a 40-second drift. You can follow that in the event log. We can follow this along for a bit. and that's 40 seconds, and then that timestamp will change with the transient measurement. We can see that progress through. So we've separated out the data acquisition software, and it gives us this freedom to have so much more capability. And on here we see a condensed version of all the experiments that are running, and if we have multiple channels going, that experiment list will show all the different experiments that are scheduled and or in progress inside the schedule. So here we can see a nice package demonstrating the power of the channels and the MP-1. And then we separate that out from the analysis application to give us full capability to take advantage of that volume of data in a very convenient manner. And in here, of course, you could do the default calculations. So where we measure the contact resistance between the sensor and sample, you don't have to manually select the time off the front. That's all done. But if you want to, you can manually select the points and look at the effects of contact resistance and your probing depth, etc. So we're well within what we have available. See, our probing depth radially is 14 millimeters from the edge of the sensor. I think we had approximately that much. The green is telling us we did. In axial, we're well within the probing depth of the thickness, which was 9 millimeters. So test 1 is being measured. So we finished the drift recording. Now running test 1, we can follow that along, and then I'll end the demonstration. So this test only 5 seconds. So if there's any questions, or if you guys want to contact us on making some measurements or seeing a one-on-one demonstration, we're happy to do that. So it's making this measurement. That is the recorded temperature of the room. There's our transient of temperature rise versus time and our residuals. You can see our axial is 1.4 and our radial is 28 watts per Kelvin. That's in the, again, we encourage you to use the full analysis application to review the data to make sure you have a good fitting. So that concludes the demonstration. If you have any questions, please get a hold of us, and look forward to the next demonstration.